What if I told you that the universe we live in actually has a built-in limit? Seriously, a limit so fundamental and so deeply baked into the absolute fabric of reality that not even the most advanced, mind-bending technology of the future could ever overcome it. Well, get ready, because today we're exploring one of the most fascinating and kind of reality-shattering concepts in all of science, the Heisenberg Uncertainty Principle. Think about it like this. Imagine you're trying to measure the exact position of a tiny electron. Here's the wild part. The more accurately you find where that electron is, the less you can possibly know about where it's going. And this isn't because our microscopes, our lasers, or our measuring tools are bad. Not at all. It's because nature itself literally refuses to reveal both pieces of information at the exact same time. It's a hard cosmic limit. Okay, let's dive into this explainer. Here's our roadmap for unraveling this bizarre quantum rule today. We're going to cover 1. The clockwork illusion, 2. Heisenberg's discovery, 3. The measurement problem, 4. Macro versus micro, and 5. Why uncertainty shapes reality. Starting right off with Section 1, the clockwork illusion. So, to truly appreciate how wild the quantum world is, we kind of have to establish the baseline of classical physics first. For centuries, right, physicists pursued the stream of perfect measurement. They firmly believed that if we just measured everything accurately enough, we could perfectly predict the future. This is the idea of Newton's clockwork universe, and honestly, it worked beautifully for massive, predictable things. We're talking the steady orbit of planets, the arc of a thrown baseball, or speeding rockets. If you just knew the starting position and the speed of the parts, you could predict exactly what would happen next. But when scientists finally developed the tools to look deep inside the atom, that predictable clockwork completely shattered. Inside the quantum reality, things were entirely unpredictable in the traditional sense. Which brings us to Section 2, Heisenberg's discovery. The year was 1927, and the world of physics was about to get a massive plot twist, all courtesy of the brilliant German physicist Werner Heisenberg. He realized that quantum particles just do not allow us to know everything at once. The Heisenberg Uncertainty Principle states that there's this fundamental trade-off. The more precisely you know a quantum particle's position, the less precisely you can know its momentum, and vice versa. Like I said, nature itself refuses to give up both secrets simultaneously. And this leads us to one of the most famous equations in all of science. Delta x times delta p is greater than or equal to h bar divided by 2. Now hang on, don't be intimidated by the math here. This mathematical truth is actually incredibly profound, and we're going to decode it together right now. All right, let's break these variables down. Delta x is simply the uncertainty in our particle's position. Delta p, that's the uncertainty in its momentum, which, if you remember, is basically its mass times its velocity. And that little symbol on the bottom row, h bar, that is Planck's constant divided by 2 pi. What this reveals is a really strict inverse relationship. Think of it kind of like a giant cosmic seesaw. If your uncertainty in position gets very, very small, meaning you know almost exactly where the particle is, then your uncertainty in momentum absolutely must become incredibly large to keep the equation true. Nature simply does not allow both uncertainties to hit zero simultaneously. Moving on to Section 3, the measurement problem. Okay, so we know the math now, but let's explore the physical mechanics of why this actually happens. Imagine you're trying to see one single electron. Step 1, to observe it, you have to bounce light off of it, right? Step 2, well, that light isn't just a simple wave. It's made of tiny packets of energy called photons, and those photons physically strike the tiny electron. And step 3, that physical impact instantly changes the electron's motion. You literally cannot look at the electron without kicking it around. And that right there creates the ultimate measurement catch-22. If you use low-energy light, you don't disturb the electron very much. The trade-off? Your image is completely blurry, so you don't actually know its precise position anyway. But if you say, okay, let's switch to high-energy light, you do get a much sharper image of its exact position. The problem is, because that light has so much energy, it violently kicks the electron, completely changing its momentum. Now, while this physical disturbance explains the concept wonderfully, the deeper quantum truth is even weirder. Exact simultaneous states for both position and momentum simply do not exist in nature at all. So what does this mean? Is everything just totally random, unpredictable chaos? Well, actually, no. Quantum mechanics doesn't mean particles just bounce around randomly without any rules. Instead, particles are described by probability waves, and these are governed by the incredibly accurate Schrödinger equation. The uncertainty principle just tells us there are hard limits to the precision of certain pairs of properties. Nature isn't chaotic. It is beautifully, precisely probabilistic. Which brings us to Section 4, Macro versus Micro. It is time for a quick reality check. If this uncertainty is literally everywhere in the universe, why doesn't it completely ruin our everyday lives? Like, why don't basketballs just suddenly disappear or teleport out of bounds during a game? The answer really comes down to the staggering difference in scale between human reality and the quantum realm. Think about it. A basketball has an enormous amount of mass compared to a subatomic particle. Because of that massive scale, and because Planck's constant from our earlier equation is so unimaginably tiny, the quantum uncertainty of a basketball is effectively zero for any practical, real-world purpose. It perfectly obeys Newton's clockwork laws. But zoom way, way down into an electron. At this subatomic scale, quantum uncertainty completely dominates its behavior. The rules of reality literally change depending on the size of the object you're looking at. And finally, Section 5, Why Uncertainty Shapes Reality. So let's answer the big so what here and see how this abstract principle literally holds our universe together. This principle isn't just a quirky scientific curiosity. It actually powers reality. Without it, atoms simply wouldn't remain stable. Electrons would just crash right into the nucleus. Uncertainty is what allows electrons to occupy orbitals. It makes quantum tunneling possible. It's literally the exact mechanism that allows nuclear fusion to power our sun, giving us heat and life. And on a human level, it's why modern semiconductors inside your smartphone function at all, and it's what makes the mind-boggling processing power of quantum computers possible. Without this built-in limit, modern technology, and really the universe as we know it, just couldn't exist. Before we wrap up this explainer, we really need to dismantle the biggest misconceptions out there. The first major myth, that scientists just don't have good enough equipment yet. Nope. The fact is, uncertainty remains even with flawless, perfect technology. It is just how nature behaves. This is absolutely crucial to take away from this. It is not about human ignorance or flawed microscopes. Even if you had perfect magical technology, you still couldn't measure both perfectly. The second huge misunderstanding is the myth that quantum mechanics means everything is just totally random. But in reality, it predicts probabilities with extraordinary accuracy. The uncertainty principle is about the mathematical limits of what can be known, not some chaotic void where anything goes. It operates within a highly accurate, beautifully structured framework of probabilities. So, to summarize our incredible journey today from Newton's clockwork to Heisenberg's quantum reality, the universe is not a perfectly predictable machine, but its deepest probabilities quietly shape the technology sitting right there in your pocket and the stars burning up in the sky. It is a profound, beautiful shift from absolute certainty to a reality governed by wave functions and fundamental limits. I want to end today by leaving you with something deeply fascinating to think about. If you had a machine that could flawlessly observe just one single quantum event, what would you want to witness? Would you want to see an electron's wave function in action, or perhaps watch quantum tunneling happen right before your eyes? Maybe matter meeting antimatter. Just take a second to think about the bizarre, probabilistic quantum world running quietly just beneath the surface of everything around you. Thanks for diving into this explainer with me, and hey, keep exploring the mysteries of the universe.